Hello everyone, hopefully you are doing well. We'll start up with our new lesson, Light, chapter 12, lesson 3. Have you ever thought that light actually refracts? It changes its speed when it enters from one medium to another medium. You might observe this in your homes by taking a pencil and a glass of water and putting that pencil in that glass. You can easily observe that you will see the pencil is slightly like broken or something has happened to it. On the other hand, you can have another experiment also. For example, taking a paper, drawing arrows on them in the same direction, and then taking a glass full of water and bringing that paper just down to the glass. You will see that the arrow's direction is changed. This is all due to the refraction of light. So what is light? Light from the sun travels over 90 million miles to the earth in only, let us say, 8.5 minutes. Light is the fastest thing to travel in all the universe. It is made up of vibrating electric and magnetic energy, and this energy also travels in waves. Now light, since it is a wave, it has frequency and amplitude both, as we learned about the sound waves. Light waves vibrate in direction that is perpendicular to the direction of their motion, and these kind of waves are called the transverse waves. So light travels in a wave called the transverse waves, which travel perpendicular to the direction of their motion. This is how they move, the transverse waves. Now light does not depend on just on mediums. Okay, they can travel without a medium also. For example, we learned that sound depends on medium, right? But light does not depend on medium. It can travel in vacuum such as the space. There's nothing there, no medium there, but still light is able to travel. In vacuum, light travels very fast, about 300,000 kilometers per second. Light can also travel through different mediums: air, water, liquid and solid, and gas. For example, in mediums it travels, the speed varies different. It's about 197,000 kilometers per second. Now the speed of light is so fast that some scientists think nothing travels faster than that. As I said, it's the fastest thing to travel in all universe. So today we'll also learn about the wavelength. Wavelength actually is the distance between one peak and the other peak, the next in the next wave. For example, here you see that's one peak of this wave and that's the peak of this wave. So the distance between these two peaks is called a wavelength, and when you multiply the wavelength with its frequency, you get the speed of the light. Again, the wavelength is the distance between one peak and the next in a wave. That's one peak, that's the second peak. The distance between them is called the wavelength. So you can multiply the wavelength with the frequency, by its frequency, and you get the speed of the light. Now, although light is a wave of energy, as we know that, but it is also a particle. How can something be both wave and a particle? Scientists were actually very confused about this question for a long time, and they performed many experiments to find out that light has properties of both waves and particles, so they can conclude it was both. Light is like particle in several ways. As we know, light travels in straight line called rays. Light does not have mass like a particle, but it does have the momentum like a particle. So when light hits an object, it acts like a tiny particle. Light can even change the direction of the atoms and other small particles. Another way that light acts as a particle can be seen in a camera film. If you see in the picture that is given in your book, which is in front of you, when the light hits the camera there, the film, it produces little dots. Over time, those dots will eventually form a original image. So particles of the light are called photons. Photon is a tiny bundle of energy by which light travels. The energy of single photon is very small. Photon of red light has only about 0.0, a lot of zeros, and 3 joules of energy. So each photon also acts like a wave with a frequency. So if a photon has higher frequency, as we said, it is going to have more energy. Now when light strikes an object's surface, photons, as we learned, that are particles of light, they bounce off at random angles. They don't just bounce off at the same angle. They bounce off at different angles, and this is actually called scattering. We see objects because light has scattered off them and entered our eyes. Because these particles do not bounce off at the same angle, instead they scatter at different angles, and this is how we see light. Sometimes when light hits an object, a photon is absorbed, and this is what makes up the 3 important properties of light different. For example, we have the transparent, translucent, and opaque objects. Now the light that is absorbed is usually transformed into heat energy. Now darker objects absorb more light than lighter objects. Light may also pass through objects. If a light is passing through an object, it's called a transparent object. On the other hand, if the light becomes blurry as it passes through an object, that's called a translucent object. And if an object allows little or no light to pass through it, it's called an opaque object. So these are 3 objects which the light can pass through or not pass through. For example, transparent, as we said, it light completely passes through it. Translucent, some of the light particles pass through it and makes it blurry. Opaque, which completely blocks the light particles from entering it. So when an object is between a light source and another object, it will cast a shadow on the other object. As you can see here, a source of light is there, there's an object, and it's between the, now this is another object, which is the wall. So this object is between them, and it is going to create a shadow over here. Now light sources can be natural, but this one here, the example, for example, this is an artificial one, a bulb. And now the shadows sometimes are bigger, sometimes they are smaller. Quite different shadows are there. For example, here you can see you have a teddy bear here with a source of light, an artificial light. You see that the larger shadow is there when the toy is closer to the light, and on the other hand, here you see a smaller shadow when the toy is further from the light, and then there's a tiny shadow when the toy is long away from the light. So this all depends on the angles and on the distance. Now here, for example, we're talking about small distance, but if we talk about the sun, since you know that it reflects on the earth in different angles. If the sun is low in the sky, light from the sun travels toward you at a small angle, and at this angle there's a long distance between the sun hits the ground behind you. So as the sun rises, the angle of the sunlight increases, and this shortens your shadow, right? So due to these angles of the sun, your distance, your shadows, they differentiate. The simpler example as I've given you here, that how if we change the angle and distance, you see that the shadow, the size of the shadow is different. So shadows depend on the angle and the distance between a light object or light source, and between the object and the place where the shadow is casted. So these three things are actually bounded or together with each other. It depends on the angle, what angle is it hitting, and the distance between a light source, what is the distance, and the object, the distance between these two objects, and the place where the shadow is casted, for example this place, the wall. So these three things interact with each other, and this is why we have different size of shadows. So that's all for today. Thank you very much. Hopefully you understood, and please feel free to ask any question.